Hey everybody, this is your pre-calculus video on 6.5 having to do with graphing tan, cotan, cosecant, and secant. So remember that sine is 1 over cosecant, so those are related, and cosine is 1 over secant, so those are related. And then these are related also. Tan is 1 over cotan. So that's how they are related. Again, you're going to want to refer to your notes. You have your unit circle paper. You have your trig checklist for your identities and so forth. You have your sine and cosine notes. And now, and we've even gone over the graphs part, the cosine and the sine. Well, now we are doing what they call other circular parent functions. So tan is increasing throughout the whole thing. Cotan is decreasing throughout the whole thing, and it has all your properties. And it's saying both of those functions are odd. Both of those have period pi. This one generally is from negative pi halves to pi halves for the default, and this one's generally 0 to pi. But as we graph it, it's going to be repeated, several times like we've seen before. So for example, if we do tan x, it looks like that. Now, if all we did was x to the third, it would sort of look like one of them. Not perfect, but it would sort of look like one of them, but tan repeats. And then cotan would be the other direction. So cotan x is that way. Okay. And then, again, we've done this before, but just real quick, if we graph sine, and if we graph cosecant, which is the fourth one, you'll see your minimums and maximums line up like that, where the minimum of one is the maximum of the other. And we also do cosine of x matching up with sine. See right there I have cosine and cosecant. You can see that really does not work. So that's why I'm changing it to trig to secant, because the first and fourth go together, and the second and fifth go together, and the third and the sixth. Now in the bottom one, again, we're not ready for that part yet. That's give me the angle for sine if I know these two side lengths of a triangle in a fraction, or give me the angle given a certain decimal that's between -1 and 1. But we don't really care about that yet. I'm just trying to prepare you ahead of time. And now here you can see the minimum of one matches the maximum of the other. Okay, so that's for tan and cotan, as well as for secant and cosecant. Now, because these are related to cosine and sine, then both of these have 2 pi for their period. And these have range going up to -1 and then starting at 1, whereas the sine and cosine were just in between -1 and 1. And here you can also see it says secant is even and cosecant is odd. So again, tan and cotan were odd, secant was even, cosecant was odd. Okay, so let's actually go through the problems, because for the most part this is similar to what you've seen before. Now this part does have like a few variables. It has A for the amplitude, which basically tells you how steep it is. This one, which has to do with the frequency, is the W, which sometimes they call omega. In this case, they are using B, but I prefer D. That's going to be the vertical shift. The vertical shift. So again, tan and cotan were inverses, sine and cosecant were inverses, and secant and cosine were inverses. And this furthest variable is the vertical shift. I guess technically there's a horizontal shift too, but we didn't get into that yet. So why we're studying this is we're continuing our study of trig graphs to have ranges all real instead of the domain, like sine and cosine. So which two those are is tan and cotan. Those ranges are all reals. And two of them are reciprocals of sine and cosine. So anyway, there are word problems about carrying a ladder around a tight corner and a rotating beacon. So here's your properties of your tangent function. Again, you could just refer to your notes. I'm not going to read through these. The common thing or similarity between all four of these is they do have asymptotes. So also the normal parent graphs go in different directions. Tan is increasing and cotan is decreasing. And then the cosecant and secant just look like parabolas over and over again. The other part is there is a question related to the average rate of change. And so you do f of b minus f of a over b minus a. Average rate of change is also studied in calculus, but you also studied it in 8th grade and maybe even 7th. It's the change in y over the change in x. Okay, so now for the problems. The graph of secant is symmetric to the y-axis. You can refer to your notes on that or graph it. Remember, when you're graphing, you have to be in radians, not degrees. Actually, let me show you y again. Okay, there's the red ones, which are the secants. And if I just all of a sudden switch this to degrees, it looks like a flat line, and that's not right. You have to be smarter than your calculator. You know, it's not giving you an error message, so you just know to be in radian mode. Okay, so there's your red curves, and your asymptotes happen in between 1 and 2, which is technically pi halves, odd multiples of pi halves. Because remember, that's like 1.57. What you can do again, if you'd like to, is go to your table by doing Control T, go to your table settings, start your table at 0 before you change any step problem, and go to pi halves. Pi divided by 2. So here you can see it goes like, if you're going through 0, then it's going to go 1 undefined, -1 undefined, 1 undefined, and so forth. So that's odd multiples of pi halves. Now this one says, for what numbers in this interval, the big interval, -2 pi to 2 pi, does it equal -1? Well, -1 would be right there. Y equal -1. And so it's this place, which is negative pi, and this place, which is positive pi. But it wants the smallest value, and so you put negative pi. Smallest value where y equal -1. Whereas this would be the greatest. I'm not going to write the whole thing out. So, but that's the greatest value where y is -1. Now, the reason why they say things like the smallest value is because later on, the smallest is used in a pattern. For example, -pi plus the period k. Like in this case, it's secant, so -pi plus 2 pi k. Or they might say 2 pi n, but that's like the smallest value. And then repeating over and over again. Okay, and then it says within the given interval, what's the next value? That's pi. And there are no other values in this particular interval. So, of course, they could change the -1 to be +1. They could change the secant to be cosecant. They might change the interval, but I doubt it. It just depends. Okay. Now on this one, does the graph, or actually where does the graph have vertical asymptotes if it's 2 cosecant? So you would just want to graph it. I guess technically, besides graphing, well, let's graph first. I don't want to get too far ahead of myself. 2 cosecant x. There's the graph. You can kind of like see at 0, it has it. If you have your notes, you'd look at pi, which is 3.14, and so forth. Now, I just had thought about something besides just using the table. If you wanted to just go to the calculate part, first off, remember you can click Scratchpad, go up 1, and then hit clear. You can do 2 cosecant -2 pi and see what happens. And it says undefined. You can do other values. If you click up twice, then click enter, you can change this to be positive pi, for example. I put -pi, but you could do it this way as well. So you can always do it that way if you want to. You'd have to check all your values. So to one person, this may be quicker. To another, you might just want to look in your table. So Control T, set your table settings, start your table at 0. And if you're guessing on these, then, well, I mean, I'd probably put pi halves. And you could see it happens at 0, at pi, at 2 pi. If you go backwards, at -pi, and so forth. So anyway, that's pretty straightforward. Your next one wants to know where cotangent has a vertical asymptote and you want the smallest one. So this period for cotan is pi, and for sine is 2 pi. Now I know we can't actually see it on here, but it's talking about blue and red. So you'd have a cotan, which is the decreasing, and then it says sine is red, so that'd be the red wave for sine. Okay, so where is the smallest x for the vertical asymptote is before 3 pi halves, which is at pi. And the next one would be at 2 pi. And the others would have 3 pi, 4 pi, 5 pi. It's pretty self-explanatory. just your functions again could change. I bet they change cotangent to tan or to either cosecant or secant, and they could make cosine here. You know, it doesn't matter. You just have to look at what your problem is and answer that. So your interval given was from pi to 5 pi. So it's not always like 0 to 2 pi or something like that. Pay attention to your intervals. Okay, now on this one, they have -6 tan x. So first, just in general, tan is going to go up like that. But if it's a negative tan, it's going to go like that, like cotan. So I might have graphed this before for y'all. If you do tan x, it's like this. If we change it to negative tan, it reflects across the x-axis. It still goes through the origin though, which is important. But then if you go to cotan, it looks like that also. Like it looks like the negative tan, but shifted a little bit, whether it's pi fourths or pi halves. I'm going to try pi fourths, but I'm guessing and checking. Nope, pi fourths was too much. How about pi halves? That worked. So you could say tan of x equal cotan of x. Actually, I should say negative tan x equal cotan x when it is minus pi halves. So write pi halves. So use your properties though in your notes for your domain. Your domain cannot include your asymptotes. But your range of tan and cotan would be all real numbers. Okay, here's -8 cotan, which is actually going to look like a positive tan. Shifted pi halves units. You're going to have it have asymptotes at the intervals of pi. Now this part again, this would look like x naught. Okay, well, what is an integer again? An integer could be 0, an integer could be 1, 2, so forth. It cannot be a random fraction, but you also could have negatives. So -1, -2. So how you interpret this is like x naught -2 pi, -pi, 0, pi, 2 pi, you know. And it keeps going because it repeats. And again, your range is all reals. Just more of the same, except this time you have pi 15ths. So pay attention to your window, like we've said before. -30 to 30 for 2 choices. -2 pi to 2 pi for 2 choices. So be careful. The y values, like for the minimum and maximum, stayed the same. But for your x min and x max, and this x min and this x max, they were quite different. So it depends on your window, your scale, etc. Because these two graphs look alike, but this is so much different than this. So it's up to you to pick the correct graph. Now, we can also relate it like we did on the other video, saying W is pi 15ths, and you could say period equal the normal period divided by W. Now the deal is the normal period for tan and cotan is pi. So you'd say pi over 15. And so you could say that's pi over 1 over pi 15ths. So that's 15 pi over pi. So those cancel and you get 15. And so then you're showing a couple of periods worth, several actually. So that's why it would be the negative 30 to 30. So you have the right side of this one, 3 whole ones, and the left side of this one. So anyway, that's pretty self-explanatory, but there it is. Here's one with cotangent. Again, W equal 1/13, so your period would be pi over 1/13. So this time it would be 13 pi. So again, if this does not have pi, this has pi. So you'd rule out the ones with negative 2 pi to 2 pi, but you need negative 26 pi to 26 pi. Again, going backwards just a little bit, this W had pi, and so this is does not include pi. Because they're kind of like exclusive, because you can see these canceled out. Now this one's about secant, and so again, remember secant and cosecant have normal period 2 pi, and so in this case, W is 1, and so period equal the normal period over W, and so that would be 2 pi over 1 in this case, which is 2 pi. Now all of them on this, looks like negative 2 pi to 2 pi. But you're going to have to graph it. It is reflecting the x-axis. Negative 3 secant x. So there it is. It's not defined in the middle, like from here to here. So this one's defined below negative 3 and above positive 3, including those. So like negative infinity, negative 3 bracket, union 3 infinity. You remember your negative infinity and positive infinity. I'm just going to say plus and minus infinity uses parentheses, and then your negative 3 and 3 use brackets. It always goes least to greatest. And then you want to find where your asymptotes are. So you can guess and check. You can try for an odd integer, 1 pi halves. So you could do negative 3 secant, 1 pi halves. And then it's also saying over 4. And so you can just try your different values. If you want to go to here, say negative, go to negative 3 secant, 1 pi. I don't usually type the 1, but doing that on purpose so that I could change that 1 to be a 3. Okay, and you see it. Now, like we said, if you don't have this fancy calculator that shows the cosecant, secant, and cotangent, you could just graph 1 over sine, 1 over cosine, or 1 over tan to get those. Okay. So that was undefined. So guess and check, look in your calculator, either use the table or your calculate screen. Or your notes. But if it's your notes, then make sure nothing else changed. It's just repetition. Here's another one with cosecant, so that relates to sine. And the normal period is 2 pi. W is 1 in this case, so your period would be 2 pi over 1. So that's 2 pi. Because that's t equal the normal period over w. So again, if it's normal period for cosecant or secant, it's 2 pi. And again, integers for where the asymptotes are in this one. So you can see the asymptote clearly at 2 pi, at pi, at 0. So just change your window appropriately. That's all I can pretty much say on all of these. Change your window, see how it looks. Pay attention to your X-min and X-max. -3 cosecant 1/6 x. Okay, now here it just looks like that. But if I go to my window, settings, -12 pi, which is about -36, give or take, because pi is about 3, and then 12 pi. Okay, so then you can see it's like that. Okay. And again, get your asymptote halfway, 2, 4, 6, 8, no, 12. So 6 is where this asymptote is. So that makes this one 3 and that one 9. And this was multiples of 6 pi, because you can think at 0, at 6 pi, when k equal 1, it's at 12 pi when k equal 2. And then you can do your negatives, but I don't feel like doing that. And then you can also see your range example. It's not defined in the middle for the y values. It's, below and above. Here's another one for you to do with tangent. Tangent increases. Now this is shifted down 3, and so so that way it's not symmetric to the origin anymore. But again, you can just graph it and see. since it is a vertical shift down, you put the -3 outside your parentheses. So there it is. And then you change this window. Now 2 of them go -2 pi to 2 pi. Actually, just one of them. And then the others go -14 pi to 14 pi for these. And you can see that the inflection point is down 3. Inflection means where it turns, like literally right there where it changes from concave down to concave up. Changes from concave down to concave up. This is the inflection. This is the way. All right, go ahead and pick your domain properly. Guess and check, put in your values. Pay attention to whether it says odd or integer or odd integer and what these are. Same thing here. This is W is 2 pi over 9, so that means your period would be 2 pi over 2 pi over 9. So that'd be 9 times 2 pi over 2 pi, so that cancels and you just get 9. So don't choose the one with -2 pi to 2 pi. And then do this part. Now, because it did shift down, it's not going to be like negative and positive at the same number. In this case, -1 was the middle line. Because it had -1 right there. Okay. Here's another one, and your middle is y = 5. This one has like a number in front, as well as a W, as well as a vertical shift. So just graph it. Again, W is 1/8, so that means period equal the normal period over W. And this is the normal period for cotan, and so then you'd say pi over 1/8, so that's 8 pi. So again, the normal period for cotan and tan is pi. Okay. And here's another one. W is 1/6. Your period is your normal period divided by W. This is cosecant, so then you do 2 pi over 1/6, so you get 12 pi. And this shifted up by 2. So again, one of them has -2 pi to 2 pi, the others have -12 pi to 12 pi. And again, the middle was 2, like y = 2 is what I meant. So it went from 0 to 4, like below 0 to above 4. Now, this one is on the average rate of change, and so this is where you call this A and this is B. You do f of B minus f of A over B minus A. So you'd say tan pi 6 minus tan 0 over pi 6 minus 0, which is just pi 6. Now, when we go to the calculate screen, we say tan of pi 6 this is the one that's 0.577. So this is where you may have to refer to your other notes about what is that decimal. Or you can refer to your unit circle. At pi 6, we have square root of 3 over 2, comma, a half. This is cosine, this is sine. If we want tangent, that'd be sine over cosine, or you could think y over x. So your 2's would cancel, and it'd be 1 over square root of 3, which is square root of 3 over 3. Those are equivalent because, once again, we multiply by square root of 3 over square root of 3 and rationalize that like that. Some books like it in the 1 over format and some want it this way. If you want to match the paper, then you have to have the square root on top. So I wouldn't really use that part. I'd really use square root of 3 over 3. Just so you can see it. If I do square root of 3, divide by 3 as a decimal, there's your 0.577. If we just add square root of 3, that's 1.73. So the other one we needed was 0, like tan of 0. And tan of 0 is 0. Now this looks a bit tricky, but you know, the minus 0 goes away, and it really goes to 6 square root of 3 over 3 pi. See how that worked? You multiply your extremes, that's your numerator. Multiply these, that's your denominator. And then 6 over 3 is 2, so that's 2 square root of 3 over pi. And that's the way it works. And then you have one that's a piecewise function. It has 3 parts. This one just is like telling you pi 0 is a point. The reason is because it'd be like an asymptote. It looks like, yeah. Well, this one doesn't. At pi, it does at pi. This one has an asymptote at pi. This one has an asymptote at pi. This one's vertical asymptote is at pi halves. So just a reminder, or maybe this is the first time you're seeing this, go to a document, go to a graph. Now, to type something like this, you need to use this little button to the right of the 9. Then there's a little window, and there's a 3 by 3 part. Remember, absolute value was over here, but that's the 3 by 3 piece. And we want 3 pieces. We have cosecant of x, we have 0, and we have cotangent of x. Now, over here, this might be a little tricky on the two-sided limits. Now that I'm thinking about it, I might have to make this 6 parts. Let's try it this way and then learn from it. 0 less than or equal to x, less than or equal to pi. This one would just be pi. And this one would be pi less than or equal to x less than or equal to 2 pi. That didn't really help too much. Let me zoom out. Okay, so because of how I define the inequality, it doesn't like it. So I need to make this with 1, 2, 3, 4, 5 pieces. Use 5 pieces. Cosecant x, cosecant x, 0 cotangent x, and cotangent x. Now you're probably wondering, well, what is he doing? Well, I'm going to do 0 less than or equal to x. It wants a one-sided limit, not a two-sided. And then this one's going to be x. Again, I'm doing control equal for the inequality. X less than pi. This one actually is pi. That's as easy as pi. And then this one is pi less than x. And this is x less than or equal to 2 pi. Now by putting all 5 pieces, it does look right. So I have cosecant x with 0 less than or equal to x. I have cosecant x with x less than pi. I have 0 with pi. I have cotangent with with pi less than x, and I have cotangent with pi with x less than or equal to 2 pi. Here's where you can see it like very clearly, as long as there's no glare. So there it is right there. Okay. Now you're just going to want to like look at your specific window, whether it's ending with 2 pi or ending with pi. So what I would do is go to your window and make this 0 and make this 2 pi. When I did menu 4a, things just got crazy. Well, this is where the calculator may actually have a problem with it. I mean, that is the correct thing. But what you should probably learn is cosecant is the one that's going to be like a parabola, and cotangent would be the one that's going to be like coming down. So just base it on that. Maybe in a day or two I'll be able to show the graph better, but at the moment that's not really helping me too much because I don't see what their scale is. 1, 2, 3. I guess their scale is 3. See, when I do that, I don't get that. Zero less than or equal to x, x less than pi. I bet it depends on the bounds, and the calculator has a limitation on this problem. So use your properties. Use your properties. Okay, hope that helps. Have a good one.